Good morning, everyone, and welcome to MAE 209. My name is Richard Kohar, and this is Lecture 12 on the binomial distribution. So hopefully everyone can hear me okay. I'll just say hello to everyone in the chat. Perfect. Okay, excellent. So without further ado, here we go. There are types of experiments that arise so frequent, or we see them so often, that we notice that their probability distributions follow a pattern. In the next couple of lectures, we're going to see different types of probability distributions or ways of modeling an experiment. Certain experiments we see again so often that we come up with a probability distribution formula for them. Now again, when we have models, they have assumptions that are built into them, and in order to be able to use those models, we have to make sure that those assumptions are satisfied. If they're not, then it's not correctly applied to the situation and can lead to incorrect conclusions. Good morning, I see everyone in the chat. Excellent. We just finished doing our first midterm or first test, and hopefully that went well. If you have any questions or comments about that, again, feel free to send me an email about that, and we can always answer that. Okay, so we'll move on to the example. So, for instance here, there's an archer shoots an arrow 3 times. Each shot is independent, so this is important, meaning that the first shot doesn't affect the second shot, and the second shot doesn't affect the third shot, and so all of them are independent. Each arrow has a probability of 1/10 of hitting the target. So I'll probably keep saying this over and over again, but drawing a diagram helps. And in this case, drawing the diagram is the probability tree. So we'll have on the first shot, so I should label this correctly, we'll have shot 1. So on the first one, we'll either have a success, like it'll hit the target, or it will miss. So again, I'll just draw my tree diagram here. Okay, then the next one is, again, I'll have a shot 2, and each of those. Same thing here. And lastly, we'll have shot 3. Now, can you only imagine if we had 4 shots, 5 shots? Drawing the tree diagram can become tedious. So again, we're just using 3 shots, and already it's slightly tedious. So here's shot 3. So now we can start to label the probabilities on each of the arms of the tree. So here the probability would be 1/10 that it's successful, and 9/10 that the archer is successful. Or sorry, not successful, so 9/10, again, the complement. Same thing applies to here. Because these are independent, the probabilities of the first shot doesn't affect the second shot. And the same thing for the third shot. The second shot doesn't affect the third. So we'll just copy down these probabilities again. So we have the outcomes for this is, so maybe I'll put down outcomes here. So I have 3 successes. I can have 2 successes and then a miss, a hit, a miss, and a hit, hit, miss, and a hit, oh, and a miss. Okay, and we can also write down the probability of each of those outcomes. So here I have 1/10 times 1/10 times 1/10. I should say that 3 times, so that's 1/10 cubed. Here I would have 1/10 times 1/10 times 1/9. So I have 1/10 squared times 9/10. Here I'll have, again, 2 successes, so that's 1/10 squared times 9/10. Here I only have 1 success, so that will be 1/10 times 9/10 squared. Over here I have 2 hits, 1 miss. Here's 1 hit and 2 misses. Again, 1 hit, 2 misses. And lastly, I have 3 misses. Now, looking at this example, again, we've described the situation, and an archer shoots an arrow 3 times. So 1, 2, 3. Each shot is independent, so the probabilities are not changing from one to the next. And there's a probability of hitting the target is 1/10. Now, we haven't asked what the question is. So let's say, what is the probability that the archer hits the target zero, 1, 2, and 3 times. Okay, so what we can do then is I'm going to use a random variable. So we'll let x be the number of hits okay. So we'll write x over here. We'll write the value of x over here. So on this one, there's 3 successful hits. So the number of x should be, what do you think in the chat? What value should x be? Three. Yep. Good. Yep. 3. So then over here, this is why I wrote out the outcomes, so it's very easy for me to read off. So there's 2 successful hits, there's 2 here, there's 1 here, there's 2, 1, and there's 1, and there's 0. Okay, so then what we do, let's say the probability of x equals 0, Well, over here, this is the only outcome where that happens, so that would be 9/10 cubed. Or that would be, what is it? 9 cubed, which is 729 over 1,000. So that should be 0.729. Right? 729 over 1,000. We can do the same thing with probability of x equals 1. So we look over here. It happens here, here, and here. So this happens 1, 2, 3 times. And that's 1/10. Okay, so I have is 81. So 9 squared is 81, right? Times 3 gives me the 243 over 100. Sorry, no, there's 1,000 right here, right? So go. Trying to not cut off all the page, but there we go. Same thing if we look for, we have the 2's here, we have 2, 2, and 2, so there that happens 3 times. And that's 1/10 squared, 9/10 to the 1. So I get 3 times 9. So that's 27 over 1,000. So that's 0.027. And lastly, x equals 3. That only happens once up here. So that's 1/10 cubed, or that's 0.001. So we can already start to see some patterns. What I could write here is, well, let's look at the 9/10 here. We have this is cubed. This is decreasing from 3 to 2, 2 to 1, and then we're actually left with 0 here. Same thing with the 1/10. It's going from 0, 1, 2, 3. So what I could start to do is I come up with a general formula. So I see that if I have this set as x, here's my probability of success. So that's of a hit. So we can already see that it's increasing as x is increasing. So that was 0. Here's 1, 2, and 3. So that's what I'm going to do. I'm going to write the exponent here as x. Over here, we see that it's decreasing for the number of misses. So here it's, if this was 0, then it's 3. Here is 1, so that means this is 2, 1, and 0. So what we can do then is we'll say it's 9/10 to the 3. That's when it's 0. And we're going to subtract x. Here's the probability of a miss. And here is where we have to figure out what those coefficients should be. Does anyone recognize what that looks like? Or, again, we could be thinking of it like this. So how many ways can you hit 0 shots out of 3? And again, if you notice, we don't really care then when we're starting to look at the random variable, the order of the outcomes. So order does not matter. So how many ways can you hit 0 targets or 0 shots out of 3? What do you think in the chat? Yes, there's one way to do that. And again, because we see it right here. So there's only one way. But the way that we can think of that is there was 3 shots and you hit 0 of them. That's 3 choose 0. How many ways can you hit 1 shot out of 3? So what do you think in the chat then? Yeah, then it's 3. The reason for that is, so there's 3, good, because we can see right from here. 1, 2, 3, but that's 3 choose 1. Exactly 3 choose 1. So the same thing can happen here. So if I have how many ways can you hit 2 shots out of 3? Well, then that would be 3 choose 2. So that's 3. Same thing, how many ways can you choose 3 out of 3? 3 choose 3, and that's 1. So notice here that 3, 3, 3, this is the total number of shots. And that number is not changing from one to the next. The only thing that is changing is the number of shots that are successful. I should have said number of ways you can hit successful. So that's how we'll do it for this, when we'll add that coefficient here. And so I'll put 3 choose X. And everyone should be thinking, oh, okay. That's why we call it a binomial coefficient. I might have mentioned it when we were talking about combinations. So, what we can also do is, so if you prefer, so some people, let's say I'll box this in, and this is the formula for this example. So you can write the PMF like that as a formula. You can also write the PMF as a table. Something like this. Page 3. Make sure I'll label my pages. Page 2. So again, I can just copy down our numbers. And lastly, 0.001. So there's our PMF. We can also draw in a probability distribution. We can plot that. Give it a quick sketch. So something like, we'll have 0, 1, 2, up to 3. So somewhere up here is 0.729. This isn't very drawn to scale, but just a quick sketch. 2 would be quite low, same thing down here. So there is our sketch of the probability distribution. And we can also calculate the expected value. So to do the expected value, it's the value times its probability. And if we add this up, that gives you 0.3. So the archer expects to be 0.3 shots successful out of 3, which isn't great. Okay, so what's unique about this is that there was 3 conditions about this. Going back to this, we saw that the shots were independent. There was an outcome where there was a success and a failure, and that these were basically the same thing that we did on each shot. So again, we could have had shots, we could have had coin flips, we could have had rolling a die. So there's 3 main characteristics about this that is important to notice. So again, we saw 3 there's 3 conditions. So the first one being, so instead of me saying a shot, I'm going to use the word trial. So it's a little bit more arbitrary. So each trial, not necessarily a shot, but each trial has an outcome that can be labeled as success. With probability P. And a failure. And that's with the complement of the probability, so that should be 1 minus P. The second thing is that each trial is independent of each other. And lastly, that each trial is identical. So the same thing is happening. The probabilities are not changing. So the same, let's say, not necessarily an action, but the same, again, it is a trial, but the same, yeah, let's just say action. Okay. Is that characteristics just for this case, or does every binomial distribution have these? So that's the nice thing, that these are the conditions. Again, not only was it for just this example, which we were talking with the archer, but that's something that these three things happen often enough that that's why we came up with the binomial distribution. So what we'll do is we'll say let x be a random variable that follows a binomial distribution. So what we can do is, this is where some of the notation comes in. We can say that x, we use a tilde, which means it follows, and we'll use b, and there's two parameters in this, n and p. So let me just kind of annotate that over here. That means follows, and over here this would be a binomial distribution with, we'll say, n trials and p probability of success. So looking back to how we had formed this, we're going to replace 3 with n, which is our number of trials. So instead of having 3, what we'll do is we'll use n. So just kind of copying this out, we have, so the 3's are replaced with n, so instead of having 3 here, we'll have n. We'll keep the x, because that's the number of successes. And the probability of success, in this case was 1/10, we'll write this as P. And then the probability of a miss or a failure would be 1 minus P. So the nice thing about this is that we don't have to then draw that tree diagram if we had a lot of trials, 4, 5, 6. That probability tree can get very unwieldy very quickly. So we can bypass using those tree diagrams, again, if those three conditions are met, that the outcome can be labeled success or failure, each trial is independent, and that each trial is identical. Along with this, if we have a binomial distribution, the nice thing is that we also know what the expected value is. So in this case, it's the number of trials times the probability of success. And the variance is equal to the number of trials times the probability of success times the probability of failure. Now just be very careful. These e to the x and the var formula apply only to the binomial distribution. Okay? If it's not a binomial distribution, then you have to go back and use the general formula. We have to use the definition of the expected value and the variance. Okay. Now, I should write on here. And again, this would be for x is an element of from 0, 1, 2, all the way up to n. Now let's jump over onto this example, something a little bit more engineering. It's known that any item produced by a certain machine will be defective with probability 0.2 independently of any other item. What is the probability that in a sample of 3 items at most will be in a sample of 3? Let's say at most, let's say 1. Okay, so at most is 1. So, can one make a distribution like one of a trial with more than 2 outcomes? If you have a trial with more than 2 outcomes, then it doesn't satisfy the binomial distribution and you can't apply it. So then you'll have to use your tree diagrams to do that. But it's a good question. So in this case, we'll say let x be the number of defective items in the sample. So what's interesting about this part is that the probability of success, or like air quotes, is going to be the defective items. So we see that it's 0.2. So that's the probability of success. there are going to be 3 items, so the 3 trials. So that means that we'll let x follow a binomial distribution of 3 trials with a success of 0.2. So then the required probability is x. So it says at most 1, so we're going to say x less than or equal to 1, which means that we need to calculate the probability of x equals 0 plus the probability of x equals 1. So I need to use my general formula. So for 0, I need to have 3 choose 0 times the probability of success, which is 0.2 to the 0, times the complement, 0.8 to the, in this case it's 3, plus 3 choose 1 times the probability of success happening at once, times the probability that it misses or failure, and that can happen twice. So pull out the calculator. I have 3 choose 0 times 0.2 to the 0, times 0.8 cubed plus 3 choose 1 times 0.2 times 0.8 squared. And if we add those together, we get a probability of 0.896. So again, the probability that in a sample of 3 at most will be defective is 0.896. Okay. Is there any questions before we wrap up for today? I'm just waiting to see if anyone writes in the chat. What chapters will we be covering in next lecture? That's very good. So what we were covering in this section right now was, this was covering section 3.4. So hopefully in the next lecture we'll be covering section 3.5. Yeah, we don't cover quite chapters in a single lecture, but we do cover sections. So in the next section, it should be section 3.5. And that won't be until 2 weeks from now because we'll have reading week. So thank you everyone for tuning in on this Thursday morning. And I wish you a happy reading week. So I'll be expecting everyone to be well rested and well read for our next lecture. Okay. Thank you everyone and take care. How are we for the pace of the course? We should be fine. We're going to cover the material and what was specified in the course outline. Yes. Okay, take care, everyone.